Hi, my name is Aditya and I'm the CEO of Automatsky. Today we are going to be talking about drug discovery, something called allosteric site prediction. But I'll come to that in a bit. Let me recap what has happened so far. This is our YouTube channel and you can note the URL. And on this, you will see that we had released demonstrations of production scale protein ligand docking and protein folding. Now, what are these problems and what am I going to show you today? Proteins are all over our bodies. They are responsible for all the functionality in the body. And everything in the universe tends to go to lowest energy state. So proteins fold into structures that are stable and at lowest energy state. So it's kind of an optimization problem. Now, if given a sequence of amino acids contained in a protein, you can figure out its folded structure. The structure will define the properties of the protein, what functionality it will enable or disable in the body. That is why this problem is of utmost importance in drug discovery. Now, people have been trying classical approximation methods and AI based methods, but AI based methods are basically pattern matching of structures of known protein parts in parts and trying to assemble the global structure of unknown protein. We talked to some Nobel laureates in US and Russia, and basically they are saying that all these AI methods give nonsensical answers on unknown proteins, whatever people might claim. Now, the next problem is protein ligand docking. Ligand is sounds like a complicated word, but it basically means a small molecule of a chemical or a drug. And docking with a protein basically means that protein has cavities or places in which these drug molecules can dock and bind, and then they can enable or disable functionalities of proteins, and that will enable us as humans to treat 4,000 diseases known to mankind. That is protein ligand docking, and that is also something we have demonstrated at production scale for whatever requirements we have for drug discovery. Now, recently there is a competition, and they released five problem statements: one on computational fluid dynamics, one on allosteric signal propagation, or basically allosteric site prediction, and grid expansion planning for distribution energy networks, and two more problems. Now, what they are saying is something important. They are saying protein ligand docking is great, but 85% of disease causing proteins are currently considered undruggable because they lack the deep active sites where traditional small molecule drugs can bind. So 85% of the proteins cannot have ligand binding with with molecules or chemicals or drugs. So the only viable strategy for these targets is allosteric, which is identifying hidden regulatory pockets that transmit a signal to shut down the active site from a distance. Now, classical techniques require months of simulations, and the approximations are inefficient, incapable of capturing the complex nonlinear dynamics of biological signal propagation. Now, they have provided three reference molecules and known solutions and an undruggable molecule that we have to solve for the competition. Now, we have not entered for the competition yet, but the competition will run for 6, 7, 8 months. So it's a long time. Our solution is ready. This is allosteric site prediction, and here I have implemented two algorithms: quantum walks and quantum annealers. So you can solve allosteric site prediction on using Automatsky's quantum annealers or using quantum walks on Automatsky's quantum computers. Let me describe the algorithm. Now, the implementation of quantum walks can be taken from the internet. You can take it from the Julia package. That is not an issue. Now, what we do is we replace diffusion with a quantum walk. We represent the protein as a graph and construct the adjacency matrix and evolve the adjacency matrix, and the active site becomes the starting state. Now we measure probabilities of reaching residue I. Residues showing high probability are likely allosterically connected. The advantages are that this algorithm naturally captures interference, captures multiple pathways simultaneously, and potentially fewer simulation steps. And this matches the requirements of drug discovery allosteric site prediction the closest. There could be an annular formulation where a residue is selected as an allosteric candidate, and the objective is to maximize connectivity to active site, graph centrality, path redundancy, pocket score, and minimize distance penalties and structural noise. The result is again top 5 residues, which matches the requirements of allosteric site prediction. Now, here in the drop down, I have three reference molecules with known solutions, and one is the challenge molecule. And this first tab will use quantum walks and Automatsky's quantum computers. Uh, you can set the parameters. I'm not going to explain that. Let's run the quantum walk. And here are the site predictions. And if you see the validation report, you will see that top hit count is 5 and the best known site rank is 1. You can see all the details and you can see the plot, and you can download the connectivity matrix and the contact matrix and the rankings and the report, etc. Now let us go to the annealer and I'll select the same problem and run. You can see the site predictions, and if you see the validation, the top 5 hit count is 5 and the best known site rank is 1. So it is performing extremely well, and you can see the predictions and you can download the results. Now, if I run it on the challenge problem, I have selected the challenge problem without a known solution. You can see the site predictions, and there is no validation, but you can see the predicted sites and you can download the results. Now, this is a production grade solution. The next question is what kind of resources are needed? Now, Automatsky's quantum annealers support up to 500 million qubits or Boolean variables. The version that this system is using has about 100 million qubits, but it is, and the Automatsky's quantum computer has been benchmarked on cryptography problems with 126 logical qubits and millions of gates. And we can easily push it to 300, 400 logical qubits. Now, the answer to the problem of resources is that resource estimation is a difficult problem in itself. It is like counting everything that you're going to need, and it is difficult to do with just three or four sample molecules. So, but whatever be the case, Automatsky makes the world's most powerful quantum annealers and quantum computers. So if somebody buys the solution from us, obviously he'll buy the infrastructure from us also. So that's all we had for you today. And if you have any questions, let us know how we can help you out. If you are in drug discovery, If you are interested in protein folding, ab initio protein folding, or ab initio protein ligand docking, or allosteric site protection, please let us know. Thank you very much.